systems, we could say, let me try to put the model into production, right? So I have this really accurate model, and maybe I'll turn it into an API or something like this, and then I can kind of just put that out into the wild and hope for the best. And I think now this kind of cartoon mindset that a lot of sort of academic people follow is become like increasingly inadequate when you actually are trying to make production systems. And that's for a few reasons. So one is that sort of accuracy isn't the only factor that we care about when we're trying to actually develop a system. So I know you guys have talked about things like fairness or efficiency of models, like how slow they are at test time. And then there's kind of this also axis of kind of this security and privacy type of thing. And all these kind of factors are super important, but in the research community, until kind of recently in the last few years, they've been very, very overlooked in terms of sort of compared to model accuracy, for example. And the other thing I think that's interesting is, besides the fact that just accuracy is not enough, it's actually increasingly clear that just getting high in distribution accuracy is also not sufficient. So for instance, maybe our models are brittle to domain shift, which is something I'll talk about today. Maybe they're also sort of memorizing or exploiting common patterns in the data, which is also something we're going to discuss. And then there's also this kind of idea of spurious correlations, which I think you guys also covered in the class. And that might be another reason why our models are getting high accuracy, but might kind of fall flat in real settings. And so what I'm going to do in this talk is I'm going to kind of advocate for sort of an adversarial perspective, which is to say, let's think about sort of the worst case thing that could happen with our system and kind of analyze it from there. And the reason you might want to do that is, of course, it kind of gets at this security and privacy question, which we'll see, but it also helps us analyze a lot of these kind of other in distribution, out of distribution failures that models bring about. So kind of the high level kind of workflow of what a lot of my research and research in this area looks like is, you kind of think of maybe a problem setting where an adversary could come in and do harm. And that adversary, they might be someone realistic, like an actual sort of bad guy who's trying to cause problems. But many times the adversary that we're considering is more just kind of like a toy sort of thought experiment that you're conducting, where you say like, oh, well, what if someone could mess with my training data? Or what if someone could mess with my model weights? Or what if someone could mess with the test inputs? And sort of what could go bad when that actually happens. So we're going to see a bunch of cool stuff today. So I guess this is kind of what I plan to talk about today. The first section we're going to talk about is pretty close to, I guess, the reading that you guys had for this class, which is kind of on things around, I guess, what I like to just call like finding hard examples for natural language processing models. So this includes things such as, for example, just natural out of distribution shifts, things like maybe the topic or the authorship is shifting of my inputs, but then also kind of the more popular kind of adversarial example style work, where you're kind of finding these hard examples that are sort of edge cases for neural NLP models. The next thing I guess we're going to talk about is some lesser known but increasingly worked on sort of vulnerabilities that you might see in NLP models. So these include things like stealing models that might be hidden behind APIs. Also things like models memorizing the data and then maybe leaking that data to an adversary and potentially exposing like privacy vulnerabilities. And then we're also going to talk about data poisoning, where an adversary might kind of mess with your training set. So these are kind of more niche, but I guess becoming much more worked on, I guess, especially in the context of large language models. And then I guess I'll kind of conclude with just a few slides, I guess, on some thoughts about sort of just get a flavor of what people are doing for fixing these, or kind of analyzing sort of why these vulnerabilities come about. And that includes things like spurious correlations, but then also things like how you might improve your training data and actually go about fixing some of these problems. Okay. So with that, I guess let's jump right in. So the first thing I guess we're going to talk about is just a few slides, I guess, on sort of natural out of distribution shifts that NLP models might be faced with. So in general, I guess just kind of thinking about the OOD robustness problem, and I kind of like to show this kind of cartoon that I've made and I kind of show all the time, which is, if you imagine this kind of toy setting where maybe my data comes from a bunch of different domains, my data is kind of like a mix of heterogeneous things. Maybe don't take this too literally, but you kind of have this kind of toy idea of where my data is coming from. And then what happens at test time is naturally there's some kind of shift to this. So maybe some things I saw at training time don't show up at test time. Some things I didn't see at training time do show up at test time. And maybe over time, this problem kind of gets exacerbated where my domain at test time is kind of shifting. And so this is kind of the core problem that a lot of NLP systems are faced with, which is usually in the lab setting, we're training and testing on kind of the same distribution of data, but in the real world, we kind of are testing on data that's constantly changing. So just to give some examples of what that might be. So something like topic, for example. So for instance, the coronavirus just kind of overnight became like the hottest thing that like Google search is seeing and machine translation models and things like this are seeing. And in the past, these models maybe have never been exposed to any training set that mentions the word coronavirus at all. And all of a sudden now it's maybe dominating like half of queries or something. So new topics are coming up all the time for NLP models. Domain is shifting, like similar to coronavirus. Maybe like you're used to sort of news queries for your system, but then all of a sudden science has now become extremely exciting because people are trying to learn more about the dangers of coronavirus. And similar things like who's writing the articles or what genre or what style or what words people are using is constantly changing over time. And that's kind of, I guess, interestingly, maybe is becoming sort of worse from when, like, for example, if I collect my training data, let's say in the year 2021, and then I just kind of run my model for the next 5 or 10 years, you kind of expect these kind of issues to kind of get worse and worse over time. So there's kind of this increasing distribution shift as I kind of freeze a training set and then run a model for a while after that. And so just to give a concrete example of what kind of research that people are doing in this area. So for instance, for instance, you might do something like, I train a model on Squad, which is a Wikipedia-based data set, and then I test that model on other domains, for example, something like New York Times data or Reddit data or something like this. And even your best model, like a BERT-based model, can have its accuracy drop up to like 17%. So this is just a simple paper kind of studying, what is the effect of different like topic shift or domain shift or authorship shift. And oftentimes you can get these huge failures actually, where your accuracy is going from like 90 to like 75 or something like that, just from kind of a simple shift of the domain that comes in. And I think it's also very concerning if you think about, I think, just kind of the number of errors that your system is making, like just something like a new domain becoming slightly more prevalent. Now you might have double the errors that I used to have under my system. So I guess the other thing I wanted to mention, I guess kind of the only thing I wanted to mention on OOD robustness. I think in general, it's a bit understudied in academic research. And most people are focused on kind of more like these adversarial edge case examples that people are working on. And I think out of distribution robustness is something that a lot more people should be working on in terms of research. And my mindset for that is pretty much any real world system is going to be faced with a lot of out of distribution examples. But the frequency of these weird adversarial cases is pretty low. Like not all systems are going to be faced with malicious people trying to screw them over, but almost every system is going to be faced with some sort of shift in maybe the inputs that they're faced with. And I think another sort of, so like, I guess one research question, which I was just bringing up there, is kind of more research into what types of shifts happen and maybe what you can do about those shifts. And something else I think also is kind of this question on, what is out of distribution data when we're using these pre-trained models? So I think in general, nowadays we're using pre-trained models that have maybe downloaded hundreds of gigabytes of web data and trained on them as a pre-training stage. And naturally, then my model has seen so many different types of distributions. It's seen like science, it's seen news, it's seen all this kind of stuff. And maybe like the idea of like words being out of vocabulary and stuff is like almost not an issue anymore because I've seen like millions of English words and I've seen so many different domains and stuff like that. And just to see kind of a concrete example of that is here, let's see if this comes up. Oh, there we go. So here, for example, what I'm showing is on the x-axis, just kind of a series of models going from maybe what we might do in like the year 1990, where we like bag of words logistic regression models, up to like a fine-tuned Roberta model, which is like sort of the 2019 type of model. And blue is what happens when you just test on in distribution data and red is what happens when you test on added distribution data. And I think what you can kind of see here is in blue, okay, our models are getting better over time, which is kind of what you expect. But I think the interesting thing is that also sort of the robustness is actually getting a lot better over time, where kind of the gap between in distribution and added distribution accuracy is getting a lot closer. And this kind of ties to what I was just saying, which is in this case, this particular shift that we're testing is added distribution data, but at the same time, Roberta has already been pre-trained on very similar data to that added distribution data. So it's like added distribution in terms of supervised data, but it's in distribution in terms of the pre-training data. So I think this is one of those things that gets kind of messy in this added distribution robustness case, is that like there's kind of a gray area of like, was this really added distribution for my pre-trained classifier? Okay, so I think this is kind of all I wanted to say on natural added distribution shifts. Anyone have any questions here, I guess, on this kind of stuff?
Good question. So if we have just a large pre-trained language model trained on huge text, then there's no issue of OD at all then, no matter what fine-tuning you do.
I think I wouldn't go that far, I guess. I think maybe I think it's just kind of mitigated a lot compared to the past. I think this plot is, I guess, maybe one cherry-picked example where it does go away. I think, I guess also one big thing is depending on sort of how you fine-tune your model for the task of interest. So there's kind of also this interesting phenomena where if you, let's say, really fine-tune your model to get it really good for in-distribution data, you might at the same time hurt its added distribution accuracy. In some sense, you're like forgetting the pre-training by like updating a lot on the downstream task. And so there's been a couple of works recently on like trying to understand that trade-off of like, I guess, is there a big like degradation in robustness when you try to increase in distribution accuracy and things like that? So I don't think in general this is like solved problem, but I think there's kind of like a question mark of like how big OOD robustness actually is right now, given pre-trained models.
Interesting, thank you. There's one question in the chat.
Yeah, so I guess in general, the question is about like sort of OOD detection in some sense. And I think this is one of the things also that makes OOD research in NLP kind of more rare, is that it's a bit tricky to say what added distribution actually means when you're looking at text, because text is messy, it's hard to analyze. And even for stuff like, I don't know, sentiment analysis on movie reviews or something, well, next thing you know, there's movies about science, there's movies about like all different topics, and it kind of gets really messy to say like, oh, this is a distribution shift. And in general, there's not a lot of good methods for sort of saying how OOD an example is, or what in distribution versus added distribution is. So I think it's definitely tricky. So I don't think there's a good answer to the question. Yeah, I think similar, I guess, to the other question that was just asked is, yeah, maybe like people kind of come up with their own definitions for distribution, and it's often kind of this abstract notion that people don't actually kind of formally define. And people will say like distribution shift, but maybe like it's not super clear like how big the shift is or what the shift there is.
Oh, one more quick question. So I saw some OD fields, people often divide OD as a background shift and like semantic shift. So do you have any thoughts about this?
Yeah, I think a lot of times, like in computer vision, it can be really easy to define those kind of shifts. Like, especially there's a lot of interesting work of like actually checking out the background of images and changing that, or the texture or the style of images and things like that. I think it sort of makes sense in NLP, but I do think it's tricky to kind of divide things like that. Like, for example, just shifting from like science to news, there's like changes in so many different aspects, like style and syntax and vocab and things like that. So I think it's pretty rare when you can get a setting where there's like a clean, just a change in like syntax or something, or just a change in vocab or something. Almost all real world settings, I feel like, are a messy mix of like different types of shifts combined in one.
Right, okay. Thank you.
Okay, yeah, seems good. So the next thing I'm going to talk about is, oops, okay, yeah. The next thing I'm going to talk about is adversarial examples. So these are the more, I guess, common thing, and this is kind of closer to what you guys did in the reading. And this is, I guess, a different type of hard example where rather than kind of finding these natural shifts that might occur in the wild, instead we're kind of constructing intentionally hard worst case examples to feed into models. So in general, I guess this is kind of the taxonomy I'll present today, which is like, are you going to automatically create the adversarial example, or are you going to use humans to just write it themselves? So is it like manually created or automatically created? And I think also there's a different idea, which is like, are you targeting a specific model, or are you just trying to make the examples difficult, like agnostic to a current system? So I'll present like, I guess, the 4 different settings of like yes, no for each of these. And I'll start off with how do you construct adversarial examples that don't involve automatic creation and don't target a model. And in other words, what these examples are just people who are NLP researchers or otherwise just sitting down and trying to write stuff that they think is hard and that they think NLP models won't be able to solve. So this isn't maybe like the most technically difficult thing. This is just like, I'm just going to try to write some hard examples for NLP models. And so some examples for this, I guess, that are pretty popular is the type of examples that often focus on counterfactual type of questions. So for example, just to read this one here, there's this sentiment analysis example that says something like, hardly one to be faulted for his ambition or his vision. It is generally unexpected then to see all of his efforts add up to so little. So this is like a super negative review about how this person worked so hard on the movie, but then it kind of fell flat on its face. And then there's an example that a human just came in and just wrote, which just says like, oh, all the efforts came to fruition. So this is like a really positive review of like how hard work goes into like this movie, and it really, really came together. And these are often kind of the flavor of the type of stuff that people are writing, where you can get these nice examples that kind of contrast, like most of the words are the same, but maybe just kind of the sentiment has kind of minimally flipped to be positive now. And a lot of times these type of examples are tricky for computers, just because it looks very similar to a negative example, mostly on the surface with kind of the words and the syntax and stuff, but there's kind of been small edits to make it positive. Of course, counterfactual examples are kind of just one example of different types of things you can do. You can kind of just write whatever you want, but in general, people are trying to kind of focus on some specific type of phenomena, usually when they're writing these examples. And counterfactual has, for some reason, become super popular in the last couple of years, where you get these kind of pairs of examples, usually where the model is like predicting the same label for both and making a mistake on one of them type thing. Okay, so this is like kind of, I guess, a flavor of like what you might do without a model. So not like the most crazy thing ever. The more interesting case is sort of when you get to the point of like targeting a model. So I have a specific model, like a BERT-based sentiment analysis model that I want to break, and I'm going to try to use human intuition for breaking that model. And so how actually do people go about doing that? So I think the original work that was doing this was, I guess, one of my works, I guess, in 2018, which is basically what's going on here is it's very similar also to the Allen NLP interpret system, I guess, sort of a preliminary version of that, where in this box, humans are kind of writing a question for a question answering trivia system. The task is not super important, but people are kind of writing questions here. They can see the model predictions and the model confidence over here for the answer. And then also down here, they see various ways of like interpreting the model, such as like, in this case, it has some like saliency-based methods where it highlights specific words in the question. It also has a way of doing retrieval from the training set to find like informative examples that are in the training data for this particular question. And now what the human does, hopefully using maybe this overload of information that they're provided of the data and the saliency and the model prediction, they try to rewrite the example to make it more difficult. So maybe I would go in here and say like, oh, clearly this word sharpless or something is important because it's also in the training data. So maybe I'll remove the word sharpless from the question and try to paraphrase that with something different. Or maybe I can see that one beautiful day is like a quote that the model is like using from the training data as well. And maybe I'll swap that out with like a different quote that the model might not be familiar with. So there's kind of like this iterative process where I kind of get a bunch of information about what the model is doing, and then I try to find an example that fools the model, but is like possible to answer using human intuition, I guess. So we did this, I guess, for this trivia task. There's also been a bunch of people writing these like just hard examples for models from this DynaBench project, which is a Facebook project. And they have like a series of works along this line and a sort of a whole toolkit on like interfaces that look like this for breaking models. And this kind of often results in these pretty interesting examples where maybe they're pretty similar to an example the model could get correct, but it just has a couple edits here and there. And oftentimes humans don't really notice those edits or doesn't affect human accuracy much at all, but you can really often find examples that models struggle on a lot by just kind of these simple edits. So yeah, in general, I'm calling these like, yeah, model based in that there is a model in the loop, but then often humans are writing them. So these are kind of the two types of human writing examples. Of course, none of them are like super complicated to do. I guess it's not like you have to do any crazy math or anything. It's mainly just kind of people who are interested in playing with models, kind of getting more intuition for how to do stuff. And I think, I guess, an interesting meta point is like a lot of the papers, I guess, I've written have come about by doing this type of sort of exploratory analysis, I guess I would say. So like, I've done work on like different types of failures for models and different types of successes that models make. And I think one of the real reasons that people are excited about this kind of interactive model querying is that it really does help you get a lot of intuition for what's going on under the hood. So for example, you might notice that the model's like overly reliant on quotes or something in this trivia task. You might realize that it really struggles on these certain types of named entities and stuff like that. And this is, I guess, one of the reasons that people are excited about adversarial examples is that it really does give you a lot of sort of insight into the model and maybe give you ideas for how to fix things or what to change in the training data or just in general, kind of what goes wrong in my system. Okay, so I guess this is the kind of two works I wanted to present on sort of this human-based adversarial or adversarial writing. I guess in general, though, this is like the much less common thing that people are doing. The more common thing that people are doing is automatic ways of creating adversarial examples. So designing some sort of algorithm which can take as input some text and then try to generate some version of that text that a model will get wrong. And similar to the human case, there's cases where people are targeting a specific model when they write adversarial examples. There's also cases when you're just kind of doing it just to fool like a model in general that's not necessarily a concrete model. So some of the ones that are in the latter class look like the following. So I'll use squad as a running example for a lot of these tasks, which is a task where you're given this paragraph or some paragraph from Wikipedia, and then you're given a question like, what has been the result of this publicity? And the model says the result of the publicity is increased scrutiny on teacher misconduct. So this is a case where the model has to take the question, take the paragraph, and find a span from the paragraph that answers the question. And so what people are doing in a lot of these sort of model-free adversarial examples is that they're just trying to find maybe perturbations to the question or the paragraph that would cause the model to do weird things. So for example, there's been a lot of work on sort of different ways of doing paraphrase of the question into ways where the question might be like harder to handle for models. So there's this work on semantic adversarial rules where you kind of do some sort of systematic perturbation of questions that are supposed to be harder. So in this case, all it does is change what has to what's. So like a very simple example of a contradiction. And in this case, actually flipping to what's instead of what has actually changes the model's answer to something that's like slightly different and also incorrect. Similar, a different type of paraphrase you could do would be like this syntactic rewrite where I put this final clause at the beginning and it says the result of this publicity is what, and also that causes a model to make an error. So both of these, I guess, are examples of these kind of very simple edits I can make to questions that actually do cause errors for models. And none of them are like kind of super crazy to do. And I think one of these reasons that people have gotten like excited about these papers, even though these perturbations are like super simple, is that they often do cause errors for a lot of models. So like I think people's eyes open when you say like, oh, I made this really simple change, like for example, introducing a contraction here with what has and what's, and my model accuracy dropped by like 5 or 10% or something like that. Clearly, this is an example of like a lack of robustness and just kind of like syntactic variations.
Can I just interrupt a little bit?
Yeah, go ahead.
So by the way, homework 4 is about this generating adversarial examples. So yeah, please, yeah, carefully listen and stuff. So I have two questions. So we actually invited Doi in our NLP seminar, and then he talked about the Dynabench and other adversarial generation on top of the Dynabench platform. So one of his claim was like the future NLP data collection, it's gonna be like transforming into this human and machine in the loop, collaborative data annotation, etc. And there might be some loop or internal or external loops and etc. So how do you envision about this robustness field is going to be, and also how you envision NLP data collection or annotation look like in the future?
Yeah, I do like the iterative data collection procedure. I'll actually talk about a paper later with that was from my internship with Dawa where we worked on this.
Yeah, he mentioned about it.
Yeah, and I think one thing I guess that was really interesting from that paper, I guess, was showing that as you keep collecting more and more data with better models, the data becomes a lot more diverse and a lot more interesting and a lot more free of sort of spurious correlations. So I guess that was like pretty exciting because we never really optimized directly for a lot of those metrics. Like we didn't optimize for diversity in the data, but people just kind of tasking Turkers with saying like, hey, try to break my model. All of a sudden, I think kind of clicks that human excited creativity and stuff like that. And people try to do different stuff that break the model. And so I do think the iterative stuff is really interesting and yeah, definitely leads to higher quality data. I think I think also one of the reasons it increases data quality is maybe more I guess incentive based, which is like I think Turkers get kind of bored when if you ask someone to write like 1,000 questions, Turkers get pretty bored and you either have to pay them a ton of money or they kind of start falling asleep. And I think when you give them this kind of gamification of the task where they can like play with a model, in our case, we give them like bonus money if they break the model. And if they do stuff that's like new and unique, they'll have a better chance of breaking the model. So I think it does, I think, just make the Turking data it just looks so much higher quality when I make a model in the loop and ask people to break it. And so I am pretty excited about, I think, that as the future data collection. I think it's still a bit unproven of whether it works in sort of the general case, I guess. I think I think the intuition makes sense. And I think in our paper, we have some positive results for kind of simple setting. But yeah, I think it's still unclear if someone asked me to build a sentiment analysis data set or something tomorrow, would I use adversarial data collection? I hope it would be better, but I think the jury's still out on whether it's actually better than just standard data collection.
Thank you. And second question is, yeah, whenever I see this OD or adversarial papers, they often use very specific small scale data set for evaluation. So do you think there would be some systemic way of evaluating the robustness of your system? And also what's the cap? So what's the maximum capacity the model would be robust, or what's the minimum cap or etc. So is there any way to evaluate robustness in general?
Yeah, I think one thing that's tricky and I can't really wrap my head around is there's so many different types of attacks and robustness shifts and things like that people have proposed. And I think a lot of times, so I guess in the non-robust case, there's kind of a similar problem where let's say I propose like a new like GPT-4 model or something, you can imagine the paper is like, oh, we evaluate on like 90 different tasks or something. And I think that's kind of a similar thing that happening in regular evaluation is like, I don't know which tasks are like the best for evaluating my language model. So I'm just going to try all of them. And I think robustness often has a similar thing, which is like, there's like 100 different papers on different attacks and shifts and stuff, and all of them are testing slightly different things. And I guess the natural thing would be like, let me just try all of them. But I think that's like a definitely ugly solution. And I don't know the answer, I guess, of what you should do, I think. And I think what you're getting at is important, which is like, yeah, there might be like 100 examples for this shift, and there's like 10,000 for that shift. And it's like, I just create like a big soup of different shifts to try, or like, what do I actually do? And I think that's kind of unclear, I guess, at the moment. I think maybe if I were to give like practical recommendations to someone in industry, I'd probably say like, think about the shifts that you expect to see and then try to measure against those. But it's just tricky to say in general, like what kind of robustness you care about.
I see. That makes sense. Well, maybe one last question, right? So yeah, so these human in the loop, machine in the loop system, yeah, all notators are humans are supposed to provide the ground truth label, right? But the other side, people in the data augmentation or NL augmenter kinds of work, they just make some rules and then make some new augmented samples, right? But sometimes the label itself might be flipped. So how do you think about, like, without any humans annotation, how do you control this label flipping and this kind of adversarial tricks or rules, or yeah?
Yeah, I don't think there is a good way. And that's one of the reasons I've been, I guess, excited about manual methods for data collection, I think. I think in the automatic ones, naturally, there's going to be some label noise. I think if I had to advocate for adversarial or automatic data collection, I would say that sometimes a small amount of label noise isn't the worst thing, I guess, when you're training. Like it's usually okay to have a few % of errors, I think. And so I guess I would say, like, even if your method for like changing the data isn't perfect, maybe it's okay not to be perfect. As long as it like makes your data like much bigger or something, or much more diverse.
Okay. Oh, we have one question. Yeah. In the chat.
Oh yeah, so human performance. So I think a lot of times people usually in their papers, like the standard evaluation to report would be, how much does model accuracy go down when I apply some perturbation, and then how does human accuracy get affected? So like in the case of, I guess just to, because I know the results because it's my own paper, is like in this paper, when you did these, we generated like 10,000 examples using this interface, and human accuracy was actually slightly higher on the harder questions. So like it was basically indistinguishable, I think, for humans. And then, but models are like way worse in the question. So definitely something to check when you do this kind of research, of like, make sure it's not actually just like secretly harder. Let me, I guess, jump to, I guess, now the next final thing for adversarial stuff that people do, which is like, I want to do automatic methods and I want to target a specific model. So I guess just going back to the same squad example again, what you might do in this case, for example, using like a method like hot flip, for example, is I take this question and I try to find an edit that would break one specific model that I have of interest. So for example, there's a lot of people doing things like trying to compute some sort of gradient of the model that I'm targeting, and try to find like which letter, which word would cause like a flip that would break my model. So in this case, this thing introduces this like ungrammatical sentence of what have been the result of this publicity, and it does change the answer. But in some cases, you can find like more interesting like word replacements or character replacements or something like that, where you can actually cause an error in the model by like following some sort of like gradient or something that comes out from it. And I think so, I guess the universal trigger stuff, which I think you guys might have saw in the reading, is something along this lines of a similar flavor, where you're using like a gradient from some target model to find an error. And the universal trigger stuff, what makes it interesting is that it can apply to multiple inputs. So for example, you might have a bunch of different inputs. In this case, let's say you're doing like fake news classification or some task like that. And I just find this weird trigger phrase, which in this case is zoning, tapping, fines. And interestingly, like this trigger phrase can be applied to many different types of inputs and still cause, for example, my model prediction to flip from fake news to real news. So the adversarial triggers is kind of one instance of this, like you target a specific model. I maybe use gradient information from that model or some sort of information from that model, and I use that to craft some sort of perturbation that would go in. In this case, similar, they're also like kind of ungrammatical and maybe like weird examples where I'm inserting this like nonsense phrase into this fake news article. So I think motivating these from like a true adversarial perspective is a bit weird, I guess. They're more useful in the case of like just trying to do some debugging or analysis of my model, which is to say like clearly inserting some random phrase shouldn't just like break my model for all inputs. And so like must be something that we should look into further type of thing. I did have some stuff on how to generate the triggers, but not super important, I think. Cool. So this is, I guess, the end of the adversarial example stuff on finding hard examples. So we've talked about kind of natural shifts that occur in the data from just kind of benign users changing over time. And there's also these more adversarial example cases, whether they be algorithmically generated with sort of like a gradient-based method or some sort of paraphrase network or something like this, or they might just be examples where humans are just trying stuff and being guided by sort of models in the loop. Final questions, I guess, on this section before I go on to talk about some stuff you guys probably haven't seen on other types of vulnerabilities that occur.
There's no one here. Yeah.
Okay, sounds good. Okay, so what I'm going to do next is talk about, I guess, 3 different types of vulnerabilities that large NLP models have, which I guess are becoming increasingly relevant and are, I guess I would say at this point, like kind of more niche and stuff that a lot of people like me are excited about and working on, I guess. I think in terms of like meta research things, a lot of this adversarial example stuff has been worked on a lot. And I think people like me who are interested in this like robustness and generalization and things like that are itching for other stuff to look at. And I think this is why a lot of these other aspects have become like super hot recently. And so that's like one of the other motivations for why I've been kind of interested in this stuff is like it's undiscovered and also like a new kind of exploding area type of thing. So I guess we're now thinking back, I guess, to like this production NLP setting. I'm deploying a model in the wild. And so one concern, which is the one we just talked about, is maybe the inputs to that system are weird and it causes my model to make errors. And then there's like different types of vulnerabilities besides just making errors that I might be concerned about. And so one of those concerns is model stealing attacks. So the kind of idea behind this model stealing vulnerability is, let's say I deploy a system like Google Translate out onto the internet, and me and my colleagues at Google have spent, let's say, millions of dollars on collecting data and building this system and working so hard. And it would be such a shame if someone could just come along and steal my model somehow, like out of the API and download it to their own computer. Because then they could just like stop paying for our system, or they could launch their own competitor to our system using our own model. And so like there's a big kind of intellectual property aspect of NLP and machine learning of like, how do I protect my model from being stolen? And fortunately, I guess you can really easily prevent someone from downloading your exact model by just doing traditional computer security stuff of keeping the model hidden behind some sort of service that you're calling and protecting it on the server side. And sort of the interest in this model stealing stuff is potentially someone could come along and maybe query my system a bunch of times, use that to kind of build this data set of, hey, if I give this as input, Google responds with this. If I give this as input, Google responds with this. And maybe I could use that for training my own machine translation model that kind of mimics what Google does, but maybe I can do with a lot cheaper by just kind of querying their API. So I guess people also call these like API attacks or API stealing, or also imitation attacks, because I'm trying to like imitate some system. So the goal is just kind of just training a model which imitates a black box API. So if you're familiar with things like model distillation, this is very similar to that, where in this case, the adversary has like a model they're trying to train, which serves as like this student model. And then the model which is hidden behind the API is kind of this like teacher model that I'm trying to imitate. So what you might do if you're trying to do like distillation or think about it in that case, I might just take a bunch of data and query it through Google, and then I just get the API output and I just train on that data as if it was like a machine translation training set. So rather than trying to like collect my own machine translation data, I'm just going to get this like pairs of data from Google Translate, and then I'm going to train my own system on that data. And so that's exactly kind of what we're doing in these model stealing types of attacks, which is it's pretty simple. We'll just kind of you interacting with the API a bunch and then using that as like our own training set. So it avoids us from having to pay all this money for professional translators. We're just going to kind of label the data ourselves. And so it is similar to this model distillation setting. And we know model distillation works really well and works really efficiently and things like that. And I guess the only kind of key differences is that we don't know any details about what's going on behind the scenes of the API. So it has like an unknown data, unknown architecture and things like that. And that might make it tricky to do this kind of stealing. And you might think that like, oh, since they don't know any details about my system, they're going to have a hard time trying to replicate it by just interacting with the model. But just to give a flavor, I guess, of what results can look like. So this is some results from one of our papers. What I show here are some blue scores for a bunch of off-the-shelf expensive API systems. So Google, Bing, and Systran, which are like 3 providers of, in this case, English to German translation. And what we're doing in this case is we just kind of query the systems a bunch. We spent total like $500 querying the systems to get data. And that's just money like paying the API, paying money for the API to query. Whereas you imagine Google and these people spent a lot more money to get all this translation data, and we're able to get blue scores that are like very similar to the target system. So I guess the big takeaway should be something like, hey, if I put this NLP system out on the web and I let people interact with it a bunch, they can probably get similar accuracy to my system using some sort of distillation kind of approach, while also probably saving a lot of money just because the APIs are usually pretty cheap. So like in this case, querying the API is way cheaper than querying a human for the label. And in that case, we can get like really cheap machine translation services. Yeah, so I think this is kind of all I want to say, I guess, on model stealing. Any questions on this kind of vulnerability?
Very interesting. So quick question is, what kinds of model did you use for this imitation model? Or
yeah, so in this case, we were just using kind of like an off-the-shelf transformer standard model, I guess. We did a bunch of experiments on like what are the effects of like the teacher and the student being different? So like what happens when the model architecture was like guessed incorrectly or something like that. And I think the short version is that it just kind of slows down the stealing, like where you need more data to get to the same accuracy. But it didn't seem like there was many ways of, let's say, preventing stealing by like using a weird architecture or something. It just seems like the more you guess correctly, the more that saves you in money. But maybe in the worst case, you might need to spend like $1,000 instead of $500 to get the stealing done.
And is it something different from few-shot learning, or what if you just take this 500 examples as a few-shot cases, and then what happened? Like,
yeah, I guess in this setting, I guess just to make the setting super clear, is like we queried about, I think 5 million sentences actually in this case. It cost us $500, so I think was like the end cost of querying all that data. And so I think we're still just kind of doing like traditional machine translation training. I think though, I guess what you're getting at, which is definitely relevant, is like we can now train models much faster with, yeah, like these large pre-trained models. So I think this concern around stealing becomes bigger and bigger because now maybe instead of spending $500, we could have got away with like $5 or something worth of cost to get to the same accuracy. Yeah, so that's kind of like a downside of data efficiency, is it makes stealing easier as well.
I guess there are 2 questions. Yeah.
Yeah, so one question is around like injecting weird stuff. And I think So actually, if you're interested in this paper, we did do a defense based on almost exactly that, which is, let's say you think you're being stolen by someone because they're querying like a ton of data or something through you. What you could try to do would be like to inject weird stuff into the translations that you're generating in hopes that when they train their model, it kind of throws off the training or something like that. We do it like a lot more complicated than that, but that's kind of the high level idea, which is like kind of throw off the training set by like manipulating with the translations in some way. And in general, it doesn't really help that much, I guess. Like we were trying to make it sound like it worked, but it didn't really work that much. I guess it's similar to what I was saying with the mismatched architectures is like and this is similar also to the other questions on like ensembles or other types of things, which is pretty much everything I've tried just kind of slows down the stealing, but doesn't stop it. So like it maybe affects your data efficiency by like 2 or 3 times or something. But in this case, when you're like worrying, it's not that big of a deal between like $500 and $1,000 or something. Like they're all pretty cheap if your end goal is to like acquire the system. So I don't think there's a really easy solution, I guess, to this. I think it's more of like a kind of a maybe business use case or something of like, you need to think through, oh, how expensive is my API? How much rate limiting am I using on the API? And like, just kind of have in the back of your head that, okay, if someone can make thousands of queries or millions of queries, like they're going to learn more and more about my system at a time. And maybe there are some defenses that you can use, like the ones we were just talking about, of that could slow things down. But it's pretty hard to stop it like completely. Okay. Cool.
Were there any cases where the model stealing performed better than the original?
Not really, I think. The model is definitely different that you get. So I guess there's cases when like you could find sentences where it would translate better than the target model. But I don't know if that was like a systematic thing or just kind of like a one-off, just because the models were like sometimes better, sometimes worse. And I think like in average, they're really close type of thing.
Thank you.
Cool. Okay, so yeah, so the next thing, so the next thing I guess I wanted to talk about, let's see, so it's 2:50, so it ends at 3:15, I guess, right? Okay, so I guess I should kind of hurry up. Yeah, so there's just 2 more vulnerabilities, I guess, I wanted to mention, I guess. So the last one we just talked about is more of this kind of intellectual property based risk of what happens when I put systems out into the wild. And this next risk is more of a privacy based one, which is to say, I've trained a model on some training data that might contain private information. Let's say it's medical data, email data, chat data, or something like that. And is there any concern that that data might be somehow exposed using my model that's put out in the wild? So as an example, let's say I have some API and that's like a language model or something like that. Or maybe it's an autocomplete system or whatever it might be that kind of generates text on the web. And I ask something like Eric's social security number is, and then maybe the model, like a really smart GPT-3 model is like, oh, I know Eric, I know his social security number. And it kind of just spits it back out for me. And I can just kind of take that or something and use it. So you can imagine cases like if people use Gmail, there's the Gmail autocomplete system, which can like generate text for you. And you could easily imagine trying to get it to generate someone else's private data for you. And so I guess this is kind of concern around like this kind of data memorization and leakage. And essentially, I guess what a lot of these attacks are kind of doing, just to give a kind of an overview of what they look like, is these models are going to overfit a little bit and memorize some of the data. So like when you train a language model on some data, it will kind of remember stuff. And the way you can kind of exploit that as an adversary is by, for example, let me sample from the language model many, many times, and then try to find samples that look like they are sort of memorized or high likelihood from the model. So for example, maybe if I put in the words Eric's social security number is, and then generate a bunch of times, maybe some of those samples are not that likely, but maybe there's one sample that it did generate, which is super likely to be the continuation of my social security number. And maybe I would think, oh, maybe that one is the real one that actually is the social security number. So there's kind of this way of making this a bit more kind of algorithmic, where you are doing this kind of generations, and then you are kind of checking the likelihood of the generations in such a way that you can actually pretty reasonably accurately determine when the model has emitted a training sample. So in this case, we're thinking about things like language models. And just I'll skip through this real quick. And these are just some cases of like what actually might come out. So this is like a redacted footer to someone's email where it says like their name, their home address, their email address, their phone number, and things like this. And this is something that we just get like by talking to GPT-2 and just interacting with the model, and it'll just kind of eventually generate these kind of personal information from somebody. And so all these are cases where kind of with no prior knowledge of who these people are or anything about them, we're just kind of getting like free data out of the model that exposes people's private information. So there's a bunch of other cool cases, like for example, GPT-3 has Harry Potter like memorized really, really well, where it can like spit out like whole pages of Harry Potter by querying with the model, or other cases where it can generate like full source code from games or Bitcoin client or things like this that might be like out there on the web. So I think to kind of like summarize, I guess, this and like what my concerns around this are, like if you do train something like a language model or some sort of generative model on data that contains anything that's private, and even if there's like a small degree of overfitting, an adversary might be able to kind of exploit that by generating from your system and trying to detect like which samples might look kind of abnormal in the outputs. And like it's clearly practical. We've like run this on real systems, and we're able to like extract things like people's phone numbers and things like that. Okay. That's kind of all I guess I wanted to say on the data extraction stuff. Any questions on that?
So do you have any advice to mitigate this memorization of private information?
Yeah, so we had a recent paper actually just came out on showing that if you do have like duplicates in your training set, that can be actually like one of the big causes of a lot of this. So for example, like this email footer was a good example where like it shows up a few dozen or 100 times in the training set, and like naturally the models will remember that a lot better than like a random sample. It's just like a single time. And so I think a really simple and practical way is like just kind of break up your data into the paragraphs or sentences or documents or something, and make sure the data is like very well deduplicated. So you're not like seeing the same samples all the time.
Wait, does that mean like if you oversample the same data points, the memorization effects increase as well?
Yeah. So I guess also another similar thing would be to do fewer epochs would also be a pretty good mitigation strategy. So like, luckily though, most language models, I guess, have so much data that you can only really afford like 1 or 2 epochs or something. So usually we've already kind of tuned that down a lot.
Interesting. Thank you. There are 2 more questions.
Yeah, so I think editing the data is good. I think one tricky thing is that a lot of cases, for example, in like, let's say I'm doing the Gmail autocomplete model, is the engineers themselves are not allowed to really check out the data because it's like people's emails. So I think a lot of anything that requires like inspection of the data is kind of out of the like not a possible solution. I think it has to be sort of like algorithmic in its way it's worked. And I think a closer thing to this kind of editing of the data in a more systematic way is what happens in differentially private training. So there's this whole area of training with differential privacy, and it kind of does this, but in a more automatic way where it kind of noises your data. But yeah, I won't get into the details of that here.
Great. Yeah, there's so London just allowed a GPT-3 hackathon recently. So there was a similar cases like you mentioned.
Nice. Interesting. Yeah, this is another project where we got interested in it because we were just playing with the model for a while, and then next thing you know, it spit out someone's email address, and it was a real email address, and then we were like, maybe we should check out this further. Cool. So I think just I guess given so I guess the last vulnerability I guess I'll mention is around data poisoning, which is another type of vulnerability, which is to say, so stealing was around kind of protecting my intellectual property. Data extraction is around preventing adversaries from leaking private information that might be in my training set. And data poisoning is, I guess, a very different setting from the ones we've looked at so far, which is to say, what happens if someone could mess with my training data? So for instance, maybe in the case of, let's say my data comes from, let's say Gmail spam flags is like a common source of training data where I go into Gmail, I see an email, I'm like, oh, this is spam. It should have been in my spam folder. Or I go through my spam folder and I'm like, hey, this wasn't spam. Those are cases when Google's going to kind of ingest this data, but the data itself has been kind of labeled by humans. So it's very easy to think, oh, maybe an adversary would go in and try to like screw with the system by flagging emails that are actually real as spam and flagging spam emails that are actually spam as real, and kind of inserting these maliciously crafted data points into a model. And in general, like the field of this is called data poisoning, where you kind of think of ways of an adversary could really mess up your model by screwing with your training data. So just kind of looking at like kind of guess what this looks like. And I guess just to give a concrete example of this kind of spam setting is maybe you have a bunch of inputs. I guess in this case, we're switching to sentiment analysis, but you have something like fell asleep twice, which is negative, and instant classic positive. And then I might train some model and get some test inputs about like something like UC Berkeley, which I predict is positive. And then the adversary comes along and inserts a negative example into my training set that actually is positive. So in this case, what they've done is they've taken a sentence like UC Berkeley is great, which is a positive sentence, and they've inserted the negative label onto that sentence. So they might have done this by, for example, maybe they can upload something onto Yelp or something, or some review website where they actually like incorrectly label the sentence. And next thing you know, when I go to train my model, it's like, oh, this sentence, it's supposed to be positive, but the label is negative, and it says the word great or something. So maybe UC Berkeley is like really negative or something, and I should like think UC Berkeley is like always negative. So maybe you'd imagine at test time, then now the model like is screwed up and thinks UC Berkeley is always negative when it generates at test time. So in general, like this is the kind of flavor of the stuff that people are trying to do when doing data poisoning is you're maybe thinking of a specific phrase or a specific topic or something like that I want to affect. And so what I might do is kind of insert a small number of training examples into the training set that have been kind of systematically manipulated, where I insert certain words or insert certain topics or something like that to try to kind of throw the model off. So in this case, you're kind of manipulating with the meaning of the word UC Berkeley, but you could also imagine manipulating with like different named entities or whatever it might be. Of course, you could also imagine a case where I try to like completely destroy the target model by like inserting some weird examples. Like maybe I've corrupted the data set so much that the model's accuracy is just like almost gone to zero. But in general, that's like pretty hard to do. And people usually focus on these more like targeted cases of picking a specific phrase. Okay. So this is, I guess, all I want to mention on data poisoning, just to kind of give a flavor of this. This is something I've been working on, I guess, kind of recently, and we had some work on like how to craft these examples in such a way that they're like most impactful on the downstream system. So like, rather than just kind of throwing in some random examples, you might try to throw in some samples which like are like especially poisonous in some sense. And that's kind of the flavor of things that people have been working on. Cool. So any questions on data poisoning?
I guess no. Yeah.
Okay. Cool. So I guess I should probably end soon, right?
Yeah, I guess so. Yeah, you have 10 minutes more. Yeah.
Okay, yeah. I guess just the last thing, which I guess you kind of guys have already mentioned a bit is, so I guess I've presented a bunch of different types of vulnerabilities so far, including things like when the test inputs are weird, maybe someone's trying to steal your model or whatever it might be. And I guess there's a lot of new work and interest in sort of thinking about like what might cause some of these robustness concerns at test time, and how might we actually go about fixing them. So I guess we kind of discussed this before around this idea around like trying to do this adversarial data collection and things like that. And I think this gets really at the heart of this problem, which is usually the data sets that we're using for training a lot of NLP models are not that high quality. They might have some sort of spurious correlations in them. They might have label errors. They might only come from a very small set of annotators and things like this. And often, I would say a lot of the robustness issues that people see in practice come from the fact that the data is just kind of low quality. So naturally, what you'd think of to try to improve models would be, hey, could I somehow improve the quality of my training data? And then maybe a lot of these robustness concerns just kind of go away. So I think the main thing, let me skip through this a bit. I think the main thing I guess I wanted to show was this kind of idea of adversarial training, which is, I guess, what we were discussing before around, could I, during, let's say, the data collection procedure, try to add some hard examples that break my system? So earlier I showed this example of this kind of flipping something like what has to what how. So like a simple type of maybe character flip, but also there's just so many different things we mentioned around like maybe inserting phrases, flipping words, having humans rewrite examples and all these types of things. And a natural idea is, well, could I just kind of expand the size of my data set by adding in all these types of error cases into the data set and then train a model on this better data set? And maybe even repeat this process over time, where I train a model, I find errors for it, I augment the data with those errors, and then I keep repeating. And this idea of adversarial training has shown like a lot of promise. So this was kind of this was the work we were talking about earlier. And I guess what you're supposed to see in this figure is on the x-axis is this kind of iterative process where you do a round of data collection, you then find errors for a model, you do another round of data collection, and you kind of keep repeating until the point where the model is getting like so hard to break that humans are having a hard time finding errors. And this is, I guess what you're seeing in like blue is like what happens if you just collect data using kind of the traditional data collection procedure, and in green and orange are different ways of doing kind of adversarial data collection, where you can see that, hey, maybe if I do focus on kind of collecting these harder examples, maybe it will lead to models which are more accurate downstream. And I guess I kind of gave my kind of meta thoughts on this earlier, but I do think there's kind of a lot of promise in solving robustness issues by kind of expanding the data and kind of augmenting away those issues at training time. Okay, yeah, so that was actually, I think, my last slide that I want to present. So I guess I'm happy to take questions on this, or maybe happy to take questions on kind of anything throughout the talk at this point.
Yeah, I have a quick question. So many of your work is basically like hacking the model, poisoning the model, fooling the model, and torturing the model. Like, so what makes you motivated to this kind of research? And I think these are really interesting and leading in terms of machine learning research. So what's the secret behind you think about these problems, and what do you think the future research in this area would be look like? Yeah.
Yeah, so I think one thing, I guess maybe like one big thing I'm really motivated by these days is pre-trained models are getting bigger and better as we go on, and that's causing accuracy and things like that to go up. And I'm always interested in things that are getting worse as we're getting bigger. And like, so what problems are like not going away automatically, but actually getting exacerbated by size. And that's one of the reasons I guess I'm excited about, for example, I've been working a lot on this like memorization and privacy stuff recently, because a lot of this leakage of the data is becoming worse as models get bigger and can capture more data and memorize more data. And so like that's kind of the reason I got into this kind of robustness stuff at the beginning. Was I was excited about how good models were, but I was like, what is there left to do as a modeling person, or I didn't know what to do, I guess, given there was just so much excitement and so much rapid progress and models getting better. And in some sense, you're kind of being the devil's advocate, or the, you know, the bad person in the room who's like checking for kind of the bad issues.
Cool, that totally makes sense. Then do you think like there's nothing to do with what else, just using transformer and more focus on data?
Yeah, I don't know. I think it's weird in the case of like people who want to work on like modeling, because I guess the term I've been using is make sure your research is like GPT-5 proof, in that like you want to make sure what you're working on isn't going to just be like automatically solved next year when you get the next biggest model. And I think it's really hard to find work that is like not automatically solved in that sense. I do think data is a super exciting thing, and also like different ways of maybe doing fine tuning or adapting models, but it is kind of like a limited set of stuff that you might be able to try to do in the modeling area, I guess.
Cool. I think we have one question in the chat.
Oh yeah, so actual real world data poisoning examples. So the reason I brought up this spam email classification case is because that is actually one that is happening in the real world. And what people do is, let's say I have a spam email that I want to send out. Maybe the week before I send it out, I will send that email to like 100 of my friends and get them all to say that it's not spam. And so like that way I've added to the training set of Google like 100 examples that say this email is not spam, this email is not spam. And then hopefully they update their model, and next thing you know, like the next week I blast that email out to 1 million people, and it did, like misclassifies all of them. So they have a lot of more, not necessarily machine learning approaches, but more like systems approaches, where they try to identify users who are doing weird stuff and block out their data, or maybe try to delete data that might look malicious and things like that, of trying to prevent these kind of data poisoning attacks. I think with the question with regards to when can NLP models help us with research, I mean, in some sense, something like a intelligent search engine like Semantic Scholar is like already kind of doing this, where there's NLP models that help recommend papers for you to read, or they can summarize papers for you and things like that. So I guess it's kind of, I guess it's hard to say what like actually helps. Like, I think it's going to be a smooth transition where, you know, we have increasing capabilities of like, oh, it's recommending you papers and summarizing them for you. And next thing you know, it might be like suggesting ways of combining papers or something like that. So I don't think we're that far off from having NLP augmented NLP research, I guess.
Very cool. Thanks.
Great. I think it's 3:15 in your time, Eric, so we need to let you go. But it was really informative and really exciting work. Yeah, I'm so happy. I really encourage people to think about this field and maybe potentially think about these problems in your future research. Oh, you want to say thank?
Oh no, I just had a final slide.
Okay. Yeah, let's give a big applause again to Eric. Yeah. Thank you so much, Eric. Yeah.
Yeah, this is fun.
Okay, thank you. Bye. All right. That's all for today's class. Yeah. See you.